Okay, thank you. Okay, so the third. So first of all, I would thank the organizers for organizing this wonderful conference and also inviting me here to speak. And it's great pleasure and honor to be here. Okay, so today I will go talk about some algebras associated with young philanthropy. So this is some letter exchange with Richard. It's going back to 1987, 37 years ago. So when I was first year student of the doctoral course, and I sent Richard our first paper on the integration of appropriate symmetric plane partitions. And Richard, this is the Richard replies. And this is not an email exchange. So this is a letter exchange. So I have to put the fragment and this cover letter into the envelope and then go to the post office. Okay. So the next one is the email exchange. It's date at 1992. So this email tells that I found our algebraic structures, the generic and the relations of the symmetry of algebra associated with the Young group multiplies, and these replies are coming from the next day, and that's a fantastic news. So, okay, so let's get the mathematics. So first, I will call the definition of differential process. So differential process was defined in the Stanley's 1988 paper. So the figure gradient process is as assumed that we have a minimum element and there are finitely many elements on each chunk. And the CP is a formal vector space with basis P and define linear map Q and VPC up and down. So the up operator sends the positive element X to the sum of all elements Y, each value covers X, and down operator is the dual of U or adjunct of U, and this UD send X to the sum of Z, Z is covered by X. Then the Stanley defines our gradient process P is our differential, the positive number. If the commutator of du minus ud equal r times the identity operator. So the fundamental example is the Young's lattice. The Young's lattice is one differential, and also it is easy to show that the product of our copy of Young's lattice is our differential. Another fundamental example is the Young's Fibonacci lattice, we denoted by y is also one differential. So I will give a definition later. So this is the 1988 paper for Stanley that the at that same time, for mean reached the same notion, almost same notion. And he thought this is Young's class. And this symbol Y is followed from the Pomin's paper, later denoted by Z1 here. So this is the Young's lattice. The Young's lattice is a set of all integer functions ordered by the containment of Peirce diagram. So this is a part of the Young's lattice. Okay, bottom element is empty function. This is 1, 2, 1, 3, 2, 1, 1, 1, and so on. So this is a familiar concept figure. The next one is the Young's lattice. The Young's lattice is as a set consisting of all finite scores of ones and twos. So we call such a body the Fibonacci board. And partially ordered given by the following covering relations. The covering relation is defined inductively. So if the 1V covers exactly the one element V, so we remove the first one here, you get the V here. And the Y of the form 2V covers W, yes. If I know only W covers V, so you see here something like that. The 1, 2, 1, 1 covers 2, 1, 1, 1. So this remove 1, then 2, 1, 2, 1, 1 covers this 2, 1, 1. And the 2, 2, 1 covers these three elements, 2, 1, 1, 1, 2, 1. The 2, because if you remove 2 here, then you get 2, 1, so 2, 1 is here. So 2, 1 is covered by these three elements. So this 2, 2, 1 covers those three elements. So this topological Fibonacci lattice is constructed from the bottom by reflecting all the Hasse diagram and extend each lattice one element above it. That's all right? Information?
Wait, yeah, two, it should be 1, 1, right? Yeah, same level of 2.
Where is that?
The level of
Sorry, that's high.
He just wanted to see if you were paying attention.
That's good. Okay, right. Okay. So first we will go to the algebraic structure associated with the Young lattice. It is classically known that the symmetric group are the algebraic structures describe the Young lattice. So the Young lattice appear, or the symmetric group appears three ways in the relation with the Young lattice. The first one is Young lattice is a blockly diet of the tower of symmetric groups. So, like I said, with symmetrical and letters and then reducible representation with complex numbers are reduced by partial square. We do not by as long the corresponding reducible representation with the partial lambda. Then the blockly diagram with tower of symmetric groups S0 and S1 is one element group and S2 is a group and so on. Then the Sn minus 1 is the subgroup Sn of fixing the last vector n. Then this blockly diagram of this tower coincides with the Hasse diagram of the algebras. That means that if you have a reduced representation of Sn, then you can restrict this representation to the subgroup Sn minus 1. Then this restricted representation is decomposed into the sum of the reduced representation of Sn minus 1 with about this d1. And also, the partition appears in this decomposition is exactly the partitions that covers by lambda. Okay. So this is the classical result. And then almost 5 years ago, Gates proved that this is the only tower of finite groups that produces a one differential process. So namely, if Z0 and Z1 and so on is a tower of finite groups, and assume that the blockly diagram of that tower is small to the one differential process, then the process should be the Young's lattice, and also the groups are the symmetric. So this is the one characterization of the Young's lattice in terms of the tower of finite groups. So the next algebraic structure is symmetric Lagos symmetric functions. Okay. So let all of Sn be the Grothendieck group of the representation of Sn that is a free Z module with basis of the isoplasties of the reduced representations, and we consider the direct sum of these Grothendieck groups. Then this Grothendieck, the reduced sum of this Grothendieck group has the associated commutative integrated structure with respect to the induced from the Sn process, Sn process Sn to the Sn plus N. And also it is known that this associated gradient link is isomorphic to the Lagos symmetric functions with the corresponding this one. So reducible corresponding to lambda maps to the shear function. Then this corresponds to the isomorphism between the gradient link with the Lagos symmetric function. The third one is the characteristic. So this group can be group or has a ring structure because SM is a group, so you can consider tensor product to representation of the same group. Then you can decompose this into the reducibles. Then the multiplicity when denoted by G lambda mu mu is called the Kronecker coefficient, and this Kronecker coefficient can be computed by using the character table symmetry. So the aim of this talk is to introduce the three algebraic structures associated with the Young Fibonacci lattice, which plays similar roles to the Young lattice or symmetry. Okay, so that answers the question in the Stanley paper. So the problem is to find a natural sequence of symmetry algebras whose Blockade diagram is Young. So I answered this question in almost 30 years ago. Okay, the answer is the following. So let Fn with associated value of the complex numbers with generators E1, E2 up to En minus 1, there are n minus 1 generators, and satisfied with these three relations. So the each EI is idempotent, almost idempotent, up to some scalar. This scalar is a parameter, xi, and also the relation between the adjacent generators EI plus 1 and the EI plus 1, that this product is equal to EI plus 1. In my original paper, this agreed with why I did this another problem, but for simplicity, we assume this is 1. Also, the I and J are problem, then the EI and EJ are copy. So if the parameters xi are generally, then this algebra Fn is a semi-simple and has dimension n factorial, and its irreducible representation is indexed by the Fibonacci word in by Fn. So this means that Fibonacci word of the entry sum is equal to n. So we denote by B. So B, the irreducible representation of this algebra Fn corresponding to the Fibonacci word B, and then the description from Fn to the Fn minus 1 of this representation B is decomposed into the multiplicity of the sum of the B used, but the U is covered by B in the Geological management. So this answers the question from this question. So this is a 30 years old cell, and then I will tell you some new developments the last year or so, this year. So the Florian Eval and Shane Scott found some diagrammatic realization, so more combinatorial description of my algebra. Then, so first we call the temporary leaf diagram. So this is the basis of the temporary leaf algebra. We call it short for TL diagram, temporary leaf diagram. That is some graph that represents the non-closing pair versions. Non-closing version into the blocks of size 2s. So that temporary leaf diagram is a graph with vertices to n, vertices 1 up to n, and n bar up to 1 bar, and also arcs connecting with those vertices, non-closing. Okay, zero is the number of TL diagrams of non-closing set pair version is equal to scattering. This is our Legion's favorite sequence. Then Florian Eval and James Scott define labeled temporary leaf diagram. So labeled one is the temporary leaf diagram with some positive integer label on each arc. So if the arc is alpha, connect the Fibonacci lattices I and J, then the level of this H alpha is positive and less than equal or the minimum of the absolute value of I and J. And also the level H alpha is congruent to this minimal value modulo 2. That is the absolute value of the I bar is I. So this is the first condition. And the second condition is that if alpha is nested in some another beta, then the value of alpha is better than of that of beta. So the two axes alpha and beta are nested in this condition holds in this order. So where in this example, this arc is nested in these arcs, so 1 is smaller than 2. Also, this arc 6 to 6 bar and 9 to 7 bar is nested, so this level is smaller than 5. But this arc 1 to 4 and this for 5 to 1 bar is not nested, so we can allow 1 and 1, the same levels. So then, the developments show that the number of levels of transparent diagram of side n, so there is a 2n bar c, then that number is equal to the n factorial. So let's F2 line is a vector space with basis consisting of level temporary diagram. So this is the n factorial dimensional vector space. Then we can equip this vector space with the algebra structure by the concatenation diagrams. So the product with these two diagrams, the first you concatenate these two diagrams. So this arc here and this arc here is joined, then you get this arc. But we have to level these arcs, so the level is on the created arc or root. So maybe with the minimal value of the levels with segments. So this has level 6 and this has level 8. So the new arc created here has level 6 because C6 is smaller than 8. And also, if you have a loop, for example, this one is also a loop. So this green is a loop here and here up to here and then so up to here. So this is a loop and the level is a minimal value of this segment. So this is 2, 3, 2, 3. So this minimal value is 2. Then this loop is removed and replaced by x2 as a parameter. Then you get some other new or level temporary diagram multiplied some parameters. Then there are many elements that this my algebra Fn is isomorphic to this or the algebra defined by diagrammatically. So the correspondence is the my generator EI maps to this or level diagram. So here is a couple of caps here with level I, and the other axis squared y, level by 1 to I minus 1 I plus 2 and to n. And also, they show that this algebra has a central algebra structure. So now we can consider the modular representation of this algebra. This is the first algebra. The second one is the analog Zayan limit geometric functions. So okay, right now Fn is a Grossman for the representation, so that has the Z module with basis of the I-square system, reducible representations, and consider the direct product of this Grossman groups. Then this has also associated gradient being structure with respect to the initial start of modules. The outer, take outer tensor, then initial start from Fm times Fn prime to the Fm plus N. So this is the construction of the symmetric case. Then it's a solar case. So this the direct sum of locality group is isomorphic to some non-commutative ring in two variables x and y. So ours is a non-commutative polynomial ring in two variables, which has a grading by equivalent is a grade degree x is 1 and degree y is 2. So then ours has a graded ring structure but non-commutative. And also we can define Young-Fibonacci analog shear functions SV here by inductively as follows. So the empty was, V is empty was, and the shear function corresponding to that was is 1, and if the word starts 1, then this formula is defined as 1 S1V, and also S2V is SV times a polynomial generator Y. So then we can show that SV is the basis of this non-commutative ring, and the map from this direct product, direct sum of the locality group to this non-commutative polynomial ring maps to the H plus of the CDS representation as corresponding to the Fibonacci value V to the Young-Fibonacci shear function corresponding to V. Then this corresponding to the isomorphic ring. And this and next one. So next we define third algebra. So before going to that part, there are what we call the Young's lattice case. The chronological coefficient is defined by using a character table symmetry group. And the character table symmetry group is a transition matrix between shear function and the power function. So in order to define the character algebra for this Young-Fibonacci algebra, we need to define power sum basis. Okay, so the Young-Fibonacci power sum function P of B is defined by this formula inductively. Then we can show that the up operator, so up operator defined in this formula, so it's a shear function maps to the sum of shear function where W is W covers B and down operator is maps to shear function as the sum of shear functions where U is covered by W. So then the up operator applied to this P, the power sum corresponding to B, and you get the P of 1 here. And if you apply the down operator to the power sum P of 1, then you get the multiply of the power sum corresponding to B, and that D operator kills the P2B. So this is analogous relation to the usual symmetric function power sums. So in the case of symmetric function, that operator is corresponding to the multiplication of the power sum corresponding to the question 1. Then the power sum corresponding to P alpha is mapped by U to the power sum corresponding to 1 unit alpha adjoint 1. And also the D down operator is a differentiation with respect to the D1, so you get your point. So this relation is example to that relation, so it might be considered a power sum. So now we can define a character table as a transition matrix between shear functions and power sum basis. So we define a character table Xn, the whose entries are chi or V alpha. So alpha is a low index and V is a front index. Then by use this formula, so if any equals, then we get this 8 by 8 matrix. At a glance, this looks like some character table, some group, but this table does not count to any finite group. We can show that.
Are there any orthogonality relations?
Yeah, for sure. So this has some orthogonalifications. For example, this lows, cumulus has the usual orthogonalization, and also each column has orthogonality with based on weight. Also, many cases can be considered as a trivial character, and this corresponding to a sign character. Then the tensor product of this sign character gives you some invertible mode. Okay, now we can define the Young Fibonacci Fibonacci coefficients in the same formula as in the Young the largest case and the symmetric group case. Where the product of 3 character values at the same conjugation plus divided by almost the alpha, but the alpha is defined by this way. Then the integrated component of this polynomial ring Rn has a structure of commutative associative ring with respect to this product. The structure constant is this Kronecker coefficient. And also this Kronecker coefficient is a non-negative integers. And also the down map, so this corresponds to this vector map. In the character ring case is a surjective ring homomorphism. So in fact, the power sum basis living in here is an idempotent to discover. Okay, so almost finished. And so I conclude my talk with some questions. The first question is there some description of my algebraic trend as a centralizer? The symmetric group appears as the centralizer of the GMN action of the tensor product with natural representations, so it might be interesting. And another question is the representation of theoretical interpretation of the future structure, the character structure of R. We define this ring structure in terms of the character of the table, that is a translation matrix, sure function, and awesome. So that is, at this moment, there is no connection between this character table with this algorithm. So the problem is that to find some direct connection with this thing, with this algebra. So the problem is to find some Hopper algebra structure or something, or the module, the category has some tensor product or something. So the second problem is solved. And the third problem is the characterization of the Young lattice. And Gates' theorem says that the Young lattice is the only one differential process coming from the power of finite. So it might be interesting to find such kind of characterization. Okay, almost that's all I want to say, except for this. So a happy birthday, Richard.